Hello students, your physics teacher Hassan Darwish with you. Now in this video 2, I will explain the motion of a horizontal elastic pendulum. This is the first pendulum we study in chapter 4, okay? And it is required for both for GS students and LS students. So let's start. Now let's look at the motion first. Let's define what the elastic pendulum is by looking at this simulation. Here in this video we have an elastic spring and a ball attached to one end of the elastic spring, okay? Now the other end of the spring is fixed to a certain rigid support, okay? Now you notice initially this spring is compressed and then released, so it oscillates or vibrates, as we said in the first video, about the equilibrium position here. Here is the equilibrium position. Now the spring is compressed to maximum and elongated here, okay? So this is the equilibrium. This is called turning point, and this turning point. As we said in the first video, the distance from the equilibrium position to the maximum displacement is called amplitude. You remember? Now at equilibrium, the kinetic energy is maximum. Why? Because x equal to 0. Okay? Let me repeat. At maximum elongation, here at maximum elongation, the kinetic energy is 0. Why? Because this is a turning point. The body stops here. Means its speed is 0. And so its kinetic energy is 0. But the potential energy is maximum here. Here it is maximum elastic potential energy. Now let's look at the energy when it passes through the equilibrium position here. Notice at equilibrium, x equal to 0, right? Means EPE equal to 0. So the energy is kinetic only and not 0, no friction. This is theoretical study, no friction. Now at maximum compression, and so this is a turning point here. At maximum compression, x is maximum, and consequently potential energy is maximum, while the speed is 0. So kinetic energy is 0. So be careful about these particular points that we often use in solving exercises, okay, on elastic pendulum. So you see turning point 1, turning point 2, and you see the equilibrium position, okay? Now look at the amplitude, which is OA equal OB. You see the amplitude? And look also at the energy, how it varies from kinetic to potential and then from potential to kinetic, right? Okay, this is the study of elastic pendulum, horizontal elastic pendulum. This is the horizontal elastic pendulum. So, horizontal elastic pendulum consists of a spring and a block attached to the free end of the spring. Here it is. Now, this is the equilibrium position O, and this is an air table. We use air table to eliminate friction. And I use x prime OX as a frame of reference to study motion. So here initially I compress the spring by pushing the block, you see, to this position. This is T equal 0. Now I'm going to release it without velocity. Let's see what happened. The block is shifted from its equilibrium position by xm and then released. It thus oscillates back and forth without the friction around O. I mean, as you see in the video. You see, the body moves around the equilibrium position. And this is called vibration or oscillation. Remember? At any time, the position of G is X. That's the position or the axis of G at any time. Means at any instant. And the algebraic value, be careful here, algebraic value of the velocity is V equal x prime, which is the derivative of x with respect to t. I said here algebraic value or algebraic value. I mean this number could be positive or negative. This is not the magnitude of the velocity. This is the algebraic value of the vector velocity. Okay? So here it is. At any time, the object, which was here at t equal to 0, has a certain abscissa from here to its center of mass, and has a certain velocity, which could be to the right or to the left, but I know is in motion. So this body is in motion. To the right or to the left doesn't matter for me. Clear? Okay. Now our objective is to determine what? The time equation, and consequently know the nature of motion. We want to find the time equation by applying what? The principle of conservation of mechanical energy. Okay, let's start. Step 1. At any t, the mechanical energy of the system, which is the spring, pendulum here, earth, kinetic energy plus gravitational potential energy plus elastic potential energy. Okay? Now if we consider the block, as we always do, as a point, I mean particle, and if we take the horizontal table as a reference for potential energy, then GPE is always 0. Okay? So this is always 0. And since the block is in motion, then its kinetic energy is half mv squared plus EP of the spring, because our system consists of the pendulum and earth. So half k x squared, okay? At any time. Don't forget that speed v is the derivative of x, time derivative. That's why we write dx over dt, which means that derivative of x with respect to time. Okay? But there are no dissipative forces, or I mean no non-conservative forces. There are no dissipative forces, I mean friction forces. Okay? By dissipative we mean here friction forces. Okay? The mechanical energy is conserved. You know that. The mechanical energy is conserved. What does this mean? It means that mechanical energy equal constant. Okay? What does this mean? If the mechanical energy is constant, derivative of the mechanical energy here, we always take time derivative. Okay? That's why I write d over dt of the mechanical energy. Be careful here. D over dt means prime. Clear? Means derivative, but with respect to time. And since the mechanical energy is constant, then the derivative is 0. Clear? So let's make derivative for this equation here. Okay? So Let's make derivative here. What do we get? Let me write implies. Half is a multiplicative constant, right? This is half. Now, what's the derivative of v squared? You know, it's like in mathematics, u squared. It is 2v prime plus half k is also a multiplicative constant. What's the derivative of x squared? And x is a function. Like when you have in mathematics u squared, derivative is 2x x prime equal 0. You see? Here, derivative 0. So what do we get now? Just let me insert. Sorry. So we get what? M, if you cancel half and half, you get M V prime plus K x prime equal to 0. But you know, in rectilinear motion, you know that A equal V prime equal X W prime, right? Because V equal X prime. So if you replace here, what do we get? We get M V X W prime. Why I write X W prime, not A? Because I want to show the differential equation. Means I want to show the function and its derivative. Plus K X V equal to 0. We can here divide by V. I mean, I can cancel V, right? Look here, you can cancel V. And what do you get? You get mx w prime plus kx equal to 0. Try to divide by the mass, which is always positive number mass. So you get this form, x w prime plus k is a constant, m is a constant, I divided by this number, x equal to 0, right? So what is this? You see here the function x, don't forget that x is a function, as any function in mathematics, function of time. So what do we have here? The function x and its second derivative. So this is what? This is a second order differential equation in x, which is of the form y w prime plus alpha squared, or omega 0 squared we now use, y equal to 0. Okay? Like what you did before. Like this. This is. Sorry. Like here. You remember this? So what is the solution of this? The solution is this equation. Clear? Okay, fine. So, whose solution is y equal a cosine or sine, as I said, doesn't matter. Omega 0 t instead of alpha plus phi. Okay? So what is the nature of motion? Instead of writing, sorry, here, y, we write x, okay? We write here x. So simple harmonic motion.